Hi, this is David Sanders with Electrician Ed. I'm presenting ground faults and GFCIs. This would be a typical circuit. It's a little bit different actually, but this represents your hot conductor on a branch circuit. This represents your neutral conductor on a branch circuit. This is a receptacle that's tied into it. Now, this is kind of weird right here because all of this stuff would not happen at every receptacle. So it's a little bit out of the ordinary. But I'm just showing this in order to demonstrate a ground fault circuit and a ground fault circuit interrupter. Some things that I didn't show in this that I kind of wish I would have drawn in is there's another grounding connection in every system, and that happens at the transformer. So outside your residence, there either be a transformer up on a pole or on a pedestal of some sort. And in the center tap on a single phase of that transformer, secondary side, it will be bonded to the earth. That will be your grounded system. That's what makes it a grounded system. So that is a connection that happens in nearly every electrical system. Not all electrical systems are grounded, but they're very special cases. Typically, this is what you're going to have. Okay. Here, this represents a ground rod. This would be your grounding electrode conductor. This is a ground bar that would be inside a main panel. It wouldn't just be floating around. You wouldn't be doing this on every branch circuit or every outlet. This small little mark right here is the main bonding jumper between the grounding system and the grounding electrode conductor. And anything that's grounded is going to come to this point, including the grounded electrode conductor, or excuse me, the grounded conductor, which is also known as the neutral. And it's known as the neutral because it's attached to the neutral point in your service transformer. So this is the path back to your source. It may go through another panel to get there back to the main panel, but in this case, this is the connection that you would see at your main panel and only there, not anywhere else, because we don't want current normally flowing on your grounding system. We want to keep that separate from your neutral. However, it has to have this little connection at least one time so that it will be an effective ground fault current path back to the source. If we didn't have this, then the earth would have to carry all of the ground fault current back over to the pole and back up. And some of that will happen, and you'll see that later on in the video. Now this is potential that's coming down, and it's just waiting right here. So between this point here and this point, we have 120 volts because that's what it is back at the transformer. 120 volts approximately by name only. So this side of every one of your receptacles is going to be hot all the time. If a child came up and found an unprotected portion of the system, this could be an adult also, but and makes contact, now we've got actual current flow. Before this was just potential, it was just an open circuit. But it's an abnormal circuit. This is a ground fault, and it's going through his arm, through his heart, down both legs. I'm showing a splitting here because at every point of contact you've got you've got multiple parallel paths through your body and also through the ground. Here's one pretty good path coming up the grounding electrode conductor through the grounding system, main bonding jumper, to the neutral conductor and back to the source. And that would be a low impedance path. And if it's a high enough current, if it's over 15 amps, if that's what's protecting the circuit, then it will trip and it will stop. But we don't want to count on that. And besides that, that is a lot of current to pass through a body. It doesn't take much to kill us. Now these other parallel paths, they're not just flying up through the air here. This is actually climbing the pole on that grounding conductor out there at the pole and going back to the source as well. So this is another path. It's all happening. Electricity doesn't just go to ground, but it goes to, it takes every path available that it can to get back to the source. We have to stop this somehow, because otherwise this person will die. We can do that by breaking the connection at any point along the way. And once the connection is broken, the current stops again. Now we've just got voltage again. And this is an open circuit again. But there's a better way to do that. If you can't let go. Normally you would, if you got shocked, you would, even if you froze up on it, the weight of your body, you would hopefully pull yourself off of that connection and stop the electrocution before you died. But we don't want to depend on that happening. So let's introduce a GFCI breaker in this case. And these hook up a special way. They either have a pigtail like this, or if it's a plug-on neutral breaker, it will just snap right into a special panel designed for it. And you don't have to worry about connecting this. But if you have a curlicue white wire coming off of your breaker, it needs to attach to the to the neutral bar in the panel. Okay, and then we also have to do something about this too. If we're going to protect this outlet, then we need to change this, because this is now our neutral connection back to the source. We need to bring this over to here. So we'll break that connection right there, and we'll join it up over here. And this wire inside the panel will attach to the breaker, and then this wire here would here I show it's just kind of like a bus bar, but for the branch circuit going out to here, this would attach to the brass colored screw on your breaker. And then since we've got potential, this is on, it's still waiting out here. And when he makes connection, we're still going to have a millisecond or two, maybe just a few milliseconds. It really depends on how much current is escaping this system. In a normal situation, we would have something plugged in here, and it would come back through this neutral wire, back through the mechanism inside here, and then back here and up there. And if everything was balanced, it would be fine. In this situation, we've got power going through the circuit, but not returning here. So it's going to trip, and it'll do that within milliseconds. It's actually based on a magnitude time curve. So how much current is going through will determine how long it takes to trip. And that helps to avoid nuisance tripping. But as soon as it detects it, it's going to trip the breaker. And then we've got the potential just waiting over here again. This is what that mechanism inside I should say the circuit inside GFCI, and this could be the breaker or it could be a receptacle. When you have a balanced circuit, you've got 10 amps going out, something is using that current, and you've got the same amount going back. This right here is called a toroidal coil. It's like a transformer, and it helps to keep magnetic fields centralized here. Now when current flows through a conductor, it creates a magnetic field around it. And here you have something going through a coil of a motor or the resistor of a light bulb or a heater or something, coming back, and it's the same amount. So this magnetic field that would be created here is in opposition because this one is directed this way, this one is directed the other way. They oppose one another and they cancel one another out. So there's zero magnetic field here. This other coil here is a sensing circuit. It would be like the secondary coil on a transformer. And the circuit will detect any voltage here that's created if there's an imbalance in the magnetic field here. That will in turn trip the relay, which will open the contacts and stop the current flow immediately, instantly. So anything that happened down here that was imbalanced, it will not continue. Here's an example of a situation where you've got current flow and it's normal. This thinks it's normal. It's got 10 amps going in, 10 amps coming back out of here. But at this point right here, he's actually got a little bit of current flowing through him back up. And in this case, it would actually look like it's balanced. But remember that we've got some current that's escaping. It's all trying to get back to the source. And if there's a path, it's going to take every path it can. That imbalance may only be 6 milliamps or less. And this would be small enough that we might not ever feel that. And also it's small enough, the magnitude, that this time curve kicks in. It might take up this 6 seconds before this trips. Now if it was like 30 milliamps or something like that, then it may only be 2 or 3 milliseconds for this thing to kick in and trip. So at this point, it's detected that we've got an imbalanced circuit, but it hasn't quite tripped yet. And now it has tripped. It's tripping, I should say. Here it is a little closer. And the imbalance was only 6 milliamps. And at this point, then we've got zero current flowing because it's opened, and nothing is getting power here. This has been David with Electrician Ed, and I just want to thank you for joining me for this explanation of what ground faults look like and also how to hook up a GFCI breaker. If you enjoyed this content, just give me a thumbs up. Thank you.